Ciao, and welcome to the Frontier Space Podcast, a dialogue about how space technology and exploration are transforming our solar system.
Welcome, Dr. Youngbay, to the Frontier Space Podcast.
Thank you for your invitation.
We're honored to have you here. We hope it's not too hot over there in the in California.
It's just beginning, so today will be like a low 80s, so it's not going to be that bad. Yeah.
Yeah, I think what you were just mentioning about keeping the next generations in mind is really important.
I think so because in fact my papers are all in ResearchGate, and I created a section there so that everybody in the world can see, and I look into the readers of my papers. Surprisingly, from small country, Zimbabwe or something like that in Africa, to all the way to almost everywhere. But I looked into the overall, it's younger generation, and I said, "Wow, thank God, you guys are working." So I've been very happy to see readership, and also the whole world is looking for something. That's the vibe I got. So I really commend you to initiate something. It's going to be very exciting and useful. So I'm willing to help you as much as I can.
That's really awesome to hear. And still learning a lot from your research publications here.
Oh yeah. So I created a lot of papers, something like 10 heavy papers I wrote, and it's going to take some time to digest, even for the rocket guys, the rocket specialists. Yeah.
Yes, can imagine.
Yeah.
Yeah, it's really enjoyed both the publications on the entitled "The Perspective of Photon Propulsion for Interstellar Flight" in the first demo of the Photonic Laser Thruster.
Oh, thank you.
Sounds like important work you're doing there. I was curious, what kind of inspired you to embark on this mission and start the YK Bay Corporation?
Well, I'm sort of a lone runner. So I didn't like that. So when I was working at the Air Force Rocket Propulsion Laboratory at Edwards Air Force Base in old days, I lived at the center of the Mojave Desert. That's like tens of miles away from the cities, nearest cities. So it's pretty remote, and you don't see any light for 10, 20 miles. So living there, I really enjoyed solitude, as well as stargazing or watching the universe. You can really see the whole universe, 360-degree view. And then suddenly the question came along, which is why God created this big universe, but we are stuck in a small Earth? Is there any reason? That's what I had in my mind, in terms of a question. And then I realized that we do not have a transportation capability. That's part of the reason. So when I, throughout my research in advanced propulsion, starting with the antimatter propulsion, that my discovery on the photonic laser thruster may provide an answer to this. It's not 100% sure yet because still it's a research topic. But anyway, so to my capacity, I analyze everything. I try to, in fact, rebuke or tear my idea down, because that's, as a scientist, that's all I have to do. But still, the idea survived. So I think we have hope, and because of that, I decided to embark on YK Bay Corporation, especially to focus on developing photonic laser thruster that I believe is very important for the next generation of humanity.
Yeah, it sounds like it. I was wondering, could you enlighten us? What is the concept of the photonic laser thruster and beam laser propulsion?
Yeah, beam laser propulsion has been around for decades. Using lasers for propelling a cell, almost like a solar cell, except you use a laser beam instead of sunlight. So that's beam laser propulsion. So in fact, a photonic laser thruster and the beam laser propulsion, okay, that's BLP, are both photonic propulsions that generate thrust or impulse by reflecting laser beams on mirrors, or you may call it cell, but it can be also mirrors, large mirrors, without using onboard propellant. So key word here is how to get rid of the propellant. That's the rocket scientists have been struggling for decades. The major difference of the is that photonic laser thruster traps and repeatedly bounces photons in an optical cavity. Optical cavity means that consists of two mirrors, so that photons can bounce back and forth between the mirrors, and these mirrors are extremely highly reflective. And in doing so, we can increase thrust generation efficiency per given energy input thousands of times, while the beam laser propulsion bounces photons only once. And so because of that, its thruster generation efficiency is extremely low. And in terms of a perspective, the incumbent propulsions, we are talking about chemical, electrical, and nuclear all together, that uses reaction mass. That means you throw a material away from the rocket to get, through that you can bounce you can have a impulse, and then you can propel rockets. So anyway, so those are the reaction mass based incumbent propulsions, and they can achieve spacecraft velocity under over 10 kilometers per second, which is about 7 miles per second. But the beam laser propulsion, BLP, becomes useful at velocities greater than 3,000 kilometers per second. That's 300 times faster than what can be achieved with the conventional rockets. That means 90,000 times or more energy is necessary, because energy required for propelling is proportional to the velocity square. So, so you imagine that you're just 10 kilometers for conventional rockets, and then you're just 3,000 or even greater for the beam laser propulsion. And there's a gigantic gap, cosmic chasm, I call it, there. And no one knows what to do with it. It's because there is no stepping stone to get there. So photonic laser thruster is created for filling the gap between 10 and then 3,000 kilometers per second. So, but in doing so, interestingly, it is projected that at velocities around 100 kilometers per second, which is about 10 times more than what conventional rockets can achieve, humanity can transform the earthbound civilization to multiplanetary civilization. So that's what my projection is. So basically, we can go anywhere in the solar system 10 times faster. That means we will be able to go to Mars, for example. Instead of a month to year, we can go. It will only take a few weeks or several weeks, then the game is completely changes because the safety increases and you don't have to carry lots of food and all those protective equipment. So the game changes there. So anyway, so threshold velocity, I believe, is for opening the multiplanetary civilization is about 100 kilometers per second. And that can be done with a photonic laser thruster in an energy and cost efficient way. So that's the keyword. So anyway, so that's the difference between beam laser propulsion and the photon laser propulsion. When the velocity goes 3,000 kilometers per second, I think there's just a little gap there, but eventually beam laser propulsion can take over. So that's the idea.
It's incredible. I think you really pioneered. It sounds like you really pioneered a lot of important research and capabilities for mankind and future generations. Yes.
Thanks for appreciating that.
You mentioned we could get to the moon and transport cargo within 14 hours with a 10 gigawatt laser.
Yeah.
7-ton payload too. Yeah.
Yeah.
But it sounds like it's definitely going to depend on the amount of the laser power and efficiency and other factors too.
Yeah. We do not have all the technologies we have, but the technologies needed to achieve all these goals are within reach of present technology. In terms of once you can be able to project it, or anyway, so that's that. And then of course they are all within the existing scientific principles. So that's the big advantages.
Awesome. And in the I think in the first demo paper, you mentioned a 10-second firing time of the laser and a 10% efficiency with a 1 gigawatt laser. Curious. So that'd be like 10 seconds of contact on the reflector or mirror spacecraft?
Yeah, depending on what kind of velocity you want and what kind of mass you have, yes. So typically, for example, when we have I think, for example, you want to have a 1 ton of a spacecraft, which would have about 50%, I would say, payload, I'm thinking. That's what you're projecting. Anyway, so that will needs about 10 gigawatts, for example. And then the contact time of the laser will be few to several hours. And then, so you are talking about over the fraction of the total distance between Mars and the Earth, you're maybe 1/10 or even less. You have the laser on, and then after that you stop the laser, and then spacecraft at high velocity, 100 kilometers per second, coast along.
This is exciting. And would this be with where would this laser be in relation to Earth?
Yeah, the laser beam. In fact, we are talking about large facility because you need to generate gigawatts power for a manned spacecraft. Of course, for just sending small cargos, you may need less than 1 gigawatt or maybe 100 megawatts, something like that, depending on the size of the cargo. But anyway, so these lasers or even power plant, you think of a gigawatts power plant on Earth, there's a nuclear power plant, something like that, So it's not going to be small. Or even the solar power, if you use the solar power, it can be much larger than even International Space Station, for example. So anyway, so this can be in the orbit. Probably sometimes it can be geostationary orbit or Lagrange points even near the Earth, and it cannot be on the Earth because photonic laser thruster cannot be operated in atmosphere. Okay, and then you can put one on the moon, for example. And for example, if you want to connect to the Mars, maybe you will have a station on the moon, and then one of the another station near the moon, is one of the small moons in Mars, for example, something like that. So all those there's many different possibilities, and where to put this power station, we are still working on it, and also it strongly depends on the mission nature.
Okay.
Mm-hmm.
And we were also curious if it would be feasible and we'd receive enough laser, efficiency and divergence and attenuation and thermal blooming from a laser here on Earth.
Yeah, the photonic laser thruster is not designed for operated in atmosphere. So all those are not relevant issues.
Okay.
So it operates in vacuum in space. So thermal blooming, all those are not an issue at all.
Okay. Sure. And so our okay, I think here and how big, how large would these mirrors be on orbit?
Yeah, the for example, Earth to Moon. Okay, there are two mirrors. One major, like a major, it's almost like a major mirror on telescope, the large one, which will be static on the powered planes. Okay, that's a primary mirror, and the secondary mirror, it will be attached to the spacecraft. So, for example, for Earth to Moon, the primary mirror diameter would be about 10 meters or so, and then on the spacecraft it will be less than 1 meter. For Mars, primary will be about hundreds or so meters, and secondary mirror will be tens of meters. Okay, so that's the size, approximate scaling. So it's not that bad if you think about it.
Yeah, no, that seems definitely attainable.
Yeah.
Nice.
And that I am about publishing another article about all these issues: thermodynamics, thermodynamics, mirror diameter, and reflection, and what kind of mirror density, area density, because that's another issue, because we do not have a good technology for doing that. Although NASA and other people studied, but then their funding was cut off, so that they, for example, gossamer structure and inflatable structure, all those may be relevant. In fact, DARPA is studying for this kind of building this kind of a structure in space. So all those things are about at the boiling points, I believe.
Yeah, it's exciting.
Yeah.
And in this demo and proof of concept you did back in 2008, what did you guys learn, and how does this inform the design of the laser here?
Yeah, we had about $500,000 to develop from scratch to develop a photonic laser thruster for large telescope, for forming large sparse, virtual telescope in space, like kilometer diameter, something like that. And so, so it was designed, for low power. We are talking about kilowatts, something like that. So anyway, use a conventional thruster, but we did a proof of concept demonstration that photon thruster can be scaled up, and then but then in doing so, I discovered that photonic laser thruster is stable against the movement of the laser mirror, which is a major discovery that no one could do that before. But anyway, so we used a typical off-the-shelf laser module. In fact, a diode pumped solid-state laser. That's the technology. And we were demonstrating, and we noticed that because we are using thin, long laser gain media, so it absorbs too much laser energy when the photons are going back and forth, because it goes through a long rod. And so that's one problem. And second problem was we, under the low budget, we could not operate this one either in the vacuum or in high quality clean room. So the data was very difficult, and then we can see much more thermal effect, something like that kind of thing, plus laser scattering effect. So there was a maximum in terms of how much we can amplify the photon thrust. So those two facts were a deficiency of that experiment, and then we used a thin disk laser. Basically, we make the laser gain media thin, so that when the photons going back and forth, the absorption becomes almost negligible. And also that we use the clean room. Vacuum is much more difficult, so we use clean room just to reduce the scattering by the dust. Those two are we learned from for the design of the high power lasers for photonic laser thruster. But eventually, I'm hoping that the whole thing can be demonstrated in space or in vacuum, large vacuum chamber, which will cost a little more money than what you used to have. But anyway, so in doing so, there will be additional increase in amplification factor. And then the details can be found in my 2021 paper about how we did 100 times scaling up of the photonic laser thruster.
Yeah, that one, that looks very interesting too. In the demo here, you mentioned you stopped a 0.75 kilogram cubesat over 2 meters here on the surface.
Yeah,
with the yttrium laser. Yes.
Yeah, the YB, yeah, ytterbium is one of the very interesting wavelength, about 1030 nanometer. And one of the most interesting material in lasers. Yeah.
Yes. And we were wondering here, why did you guys choose the active resonant optical cavity instead of the passive?
Yeah. Okay. The resonance cavity there are two types. One is passive, another is active. Passive means like a Michelson interferometer. And so, you know, the gravitational detection system uses this passive optical cavity, gravitational wave detection. When you form almost like photonic laser thruster optical cavity setup, that means 1 meter and another meter. But then when you shoot the laser from the outside, send the photon in between into the cavity, and then you get trapped photons that way. That's what they call passive optical cavity. There's no laser generating media inside of the cavity. That's used for gravitational wave detection. Why? Even if you have a very tiny, small movement of the mirror, you can detect the movement. That means as soon as you move the mirror slightly away, then thrust dies off. So that's passive. Although if you can keep it in the steady position, extremely, you know, like a fraction of a wavelength steadiness, then you can maintain power. Then you can use that. You can use that for detecting extremely small movement, even the movement caused by gravitational wave, and that is the Caltech's LIGO, okay, the gravitational wave detector. That's passive. So what it means is, although you can trap the photon, amplify the thrust, however, as soon as a spacecraft moves even fraction of a wavelength, thrust disappears, and then of course it goes further out. It may come back for a very short time. Becomes so the net average thrusts. There is no amplification. So that's passive cavity. But what I discovered is, this is accidental discovery. When I put the gain media into the cavity, that means the whole cavity becomes like a laser. It's generating its own laser inside of the cavity. Then, lo and behold, the thrust doesn't die away. So that's the difference. But using large, long-range optical cavity has begun. And we got already 1 Nobel Prize out of the gravitational detection. And then there potentially may be many different type of Nobel Prize will come if younger generation want to work on it, and that will be in space. And if we do the same thing in space with a much longer distance optical cavity, maybe you can even detect even gravitation caused by some even much smaller objects. You know, so, and all those things are amazing. And then I think the active cavity can be also used for that kind of a scientific purpose in the future. But does it make sense?
Yes, thank you for clarifying. Yeah, it's still wrapping our head around things too. It sounds like was reading. So we beam the reflector. We beam the laser to a reflector with the cargo, and you know, for several hours, and I've up to a distance of 1,000 kilometers, I think.
Moon is 1,000 kilometers. Mars is close to 1,000,000 kilometers or more.
Okay.
So 1,000,000 kilometers from here to probably our nearest Lagrange point, something like that.
Okay. And
a little more than our moon. Yeah.
It seems like we need some really high kind of, you know, steerability and high precision aiming. How could we achieve this here?
Yeah, these things surprisingly is available, you know, through the astronomy telescopes. Imagine that they are looking into the how many years behind 13.6 billion years, or now this what 10 billion years. You know, the enormous distance. They can select the stars or the, you know, whatever the black holes or whatever. They can all aim that telescope to that. So those things are available. And if you read my scientific my paper in 2012, you have some estimate there. Okay.
Nice. Yes. Okay.
Yeah. Yeah. Aiming is not an issue.
Yeah. Sounds like it.
Yeah. But there are some other issues.
Yeah. What kind of other challenges are you
Where
nice.
it's scaling up the laser. The currently about megawatt laser is available. I'm talking about in public domain, okay? And but then putting that into the space plus the scaling up that to the gigawatts level of laser will take additional challenging. You know, you're gonna put the 1,001 megawatts laser combined together, which is theoretically feasible, or you wanna do 100, 100, 10 megawatts lasers, or you wanna do 1 gigawatt laser in a single body. I don't know what would be the answer, but that's one challenge. Another is putting the building the power station with that level. Of course, moons will require about megawatts or so, or maybe 10 megawatts. And then I'm talking about in terms of sending back and forth small cargos. The main cargo may require still a gigawatts level. Anyway, so those are major challenges. And then high reflectance mirrors, large high reflectance mirrors. So far, the mirror I'm talking about, like a 4.9, that means the reflectivity is 99.99 or even better sometimes. Those has a diameters of about, let's say, meter. But how to make them bigger is another issue. So still the challenges remain.
Mm-hmm. Yeah. Anything is possible.
Yeah, they are all within scientific principle, and then also we build some foundation, some predecessors built foundation here, foundation there. So we have to connect them together and then start to work on it and build on it. But it's gonna take a lot of money. But I feel optimistic because they reduce the launch cost, SpaceX, for example, and then accessibility, and also they open the vision. Some of the major key players are already envisioning living in space somewhere, not only on Mars, but some other people think just I've been nowhere, but I believe more around the asteroid belts, something like that. So there are a lot of proven ideas are there, here and there. So it's a matter of selecting and then initiating, connecting, and pushing through.
Yes,
I believe. Yeah.
Same. What was curious here on the other types of propulsion methods available, and was curious on your thoughts on this concept of the laser thermal propulsion, and really
some of my old colleagues used to work on this one, and this is for reducing the cost of the launching, okay, because it still uses a reaction mass. So you are basically heating the reaction mass and then propel. So the difference between that kind of idea and the regular rockets, you're heating by combining oxidants. There's a very minor difference, and then eventually this kind of concept is limited by Tsiolkovsky rocket equation. That means propellant is proportional to the exponentially proportional to the rocket velocity. So I don't know whether that concept can survive in competition with the regular rocket, which is becoming more and more efficient daily. So, and I don't even know whether this kind of concept can even begin, because the already existing method is becoming much more reliable. And so the advantage is so marginal that I don't think there is any hope there. But, you know, I don't want to criticize anybody, but that's my personal opinion.
Okay. Good to know. For those of you who aren't familiar out there, the laser thermal propulsion works around the principle of you take a high power laser, and then the photons bounce off the reflector and then are concentrated into a propulsion chamber with repellent.
These are around for 20, 30 years already. The idea, you know, Jordan Kerr, one of my alumni, UC Berkeley alumni, worked on this, and we've been back and forth, and I don't see any really good reason to push this one against regular propulsion, because like what I said, because it still uses the reaction mass. You know, hydrogen is a reaction mass, so you have to push heated hydrogen out, and because of that, you have a velocity limit. So I don't see, it's basically a conventional rocket, except you replace the oxidant with the laser beam. So you want to put the oxidant there in the rocket, or you want to shine gigantic laser with lots of complex mechanism to replace that tiny portion of the oxidant. I would prefer just to use oxidant because it's proven and it's working.
Yeah, that makes sense. I was curious how much cargo and payload kilograms could we transport to Mars with a photonic laser thruster?
For example, 10 gigawatts, we can go up to 100 tons. And another beauty of the photonic laser thruster is the launch frequency is very fast, very high. So, for example, you know, it takes about 4 hours to push the laser, and then you turn off the laser, and then next spacecraft can put in, and in 4 hours, right after you can put another one. So if you think about it, it takes, let's say, 4 hours to prepare the rockets, and then the next 4 hours can be used for another one. So if you think about it, you are talking about 6 times of a launching capacity in terms of a maximum, theoretical maximum, okay? And then 6 times 365, 2,000, right? So 2,000 times per year, you can transport spacecraft with one facility, and each spacecraft, let's say, can carry, let's say, 10 tons conservatively. Then you are talking about 20,000 tons of cargo. Imagine that. That's like what 100 times of what SpaceX Starship can do in 1 year. So if you think about that, that launch frequency is amazing. Launch frequency of the photonic laser thruster. That is, I think it's revolutionized. It's almost like a train. One train goes, the next train goes, right? So I'm even thinking that you have a string of a spacecraft flying towards Mars and then coming back and forth. And then in between, maybe they can combine together, build even bigger spacecraft. By the time you are close to the destination, they can detach again, something like that. There are a lot of many interesting concepts that can come up. So anyway, so that's a major advantage that no propulsion mechanism has.
Yeah, it's really visionary here with the your the interplanetary photonic railway system.
Yeah.
It sounds like we can aerobrake around a planet or
it's not aerobrake. You need to have another one, another photon laser thruster power station at the destination.
Yes. And
then you have to use laser to slow down, because there is no mechanism that you can slow down 100 kilometers per second.
Yes.
This is extremely high speed.
Yeah.
You know, imagine that regular rocket goes 10 kilometers, and then you have not even 10 kilometers to approach Mars, much lower velocity to use aerobrake. Okay, so those concepts cannot be used.
Sorry, I meant to say like something like photonic braking or something.
Yeah, photonic braking. Yeah, aerobraking. Yeah, photonic braking. So it's exactly like some of the electric train. You send them very fast, and then you slow down at the destination. You know, so that's the reason I call it such a system. I call it a photonic railway. See, you can visualize it, right? The string of trains, boxcars are in space, going in stream, and then going one direction or another direction. And if you think about it, it's amazing.
Yeah. So you've changed my perspective.
I hope so.
And it sounds like I was curious if we could potentially, this concept of beam combining, if we could, add other frequencies like X-rays and combine them with optical frequencies to achieve a higher throughput and efficiency.
Yeah, combining with them, I'm not quite sure. But some people are saying that modulate the photonic laser beam for communicating, but I'm not quite sure about that either. But using X-ray may be interesting, because if you can develop X-ray laser, I already mentioned that in my 2012 paper, because the X-ray has much shorter wavelength, that means diffraction is much less, and it carries more momentum. Okay, so if you can develop X-ray laser in comparable beam diffraction quality, something like that would be very useful. So eventually, someday, if somebody finds X-ray laser, advanced X-ray laser, and advanced X-ray optical cavity, then mirror size will shrink by a factor of 10 or 100 even. So then it changes the game even further. So I don't know which direction it will go. One is scaling up the laser power and large laser mirror. Another is decreasing the wavelength of the laser. I don't know which would be more appropriate at this point, but I think increasing laser mirror size would be easier at this point, because X-ray laser is extremely hard to make.
Far off, but it seems like there's a lot of X-rays near stars and supernovas and black holes.
Yeah. X-ray is very common. There's no doubt about it. So I've been thinking about how to make X-ray lasers, but then even if you make X-ray lasers, then how to make an X-ray optical cavity is another issue, because there's no good way of making X-ray mirrors of a high quality. So I mean, I'm limited by existing science and technology, but then suddenly somebody will discover something, younger generation like you guys, and then something may happen. But at this point, to my knowledge, I'm limited.
Yes, the photons and optical ways. Sounds like the go-to.
Yeah.
Was wondering what think like for the next steps, what are your plans, and what kind of mission architectures and time frame for the first on orbit demo?
I have so far I think I'm in the seed stage. That means we need more manpower in terms of the guys who can work on the orbit dynamics, computer simulation of the orbits, all those things have to come by together. But first, I believe the first and also the more prominent way to demonstrate photonic laser thruster is on International Power Station, International Space Station, ISS. The reason is that it mimics the large power station that I am envisioning, the large one, either with a solar panel or nuclear power. And then the ISS has a larger solar panel on the order of 100 kilowatts. And another is that it has its own cooling system already. And so, and plus, ISS, a lot of people are watching what's happening in ISS. So it will be a very good demonstration. I proposed this one to NASA. Somehow, I don't know what is happening. They do not allow me to proceed with that. But ISS as demonstrated would be very good. And I'm thinking like a 10 to 30 kilowatts laser can be on board. And then we can prevent that transforming into some other crazy devices. But anyway, that can be used 10 plus times scaling up with the existing laser, but it will be demonstrated in space. And then it's very tangible, very feasible. Then that can be done probably in, depending on how much the funding is coming in, but 3 to 5 years.
Nice. Excellent. Well, we yeah, I think that I think we converge toward whether it be an international like power station on orbit or power beaming. I think it makes a lot of sense to get more power into orbit.
Yeah, I believe that the space solar power, and it's originally proposed for beaming the power through microwave usually on Earth, but more importantly, you can use that for photonic laser thruster, and then sending the cargos back and forth at very low cost. The problem of existing space technologies, as soon as you bring the propellant up in space, it becomes $10,000 per kilogram. Imagine that your gas, 1 gallon of gas is $50,000. Where can you go? What kind of a transportation system you can build on there, right? So getting rid of fuel is the almost important, and that's what the photonic laser thruster can do. And then on top of that, of course, the launch frequency. So you can increase cargo capacity by rapidly sending more and more and more cargos. So I think it can potentially revolutionize space civilization. In fact, that's what I would say I'm hoping.
Yeah, it's really revolutionary and inspiring to see what you're doing. Hope to support and would love to collaborate down the road. Yes.
Yeah, I would be happy to.
Well, I think that's all of our questions over here. And
okay.
Where could our listeners get in touch with you?
You can email me, or you can visit my company website. There's contact. It's a www.ykbcorp.com, ykbcorp.com, and then you can. There's a contact information. Plus, you can just directly, send messages through the online system anyway. So and then also you can go to my ResearchGate, which I put as much information as possible there.
Nice. We'll add those to the podcast description too. And thanks so much, Dr. Bay.
Oh, you're welcome, and good luck with your endeavor. You are on a very important path.
That means a lot. Yes, you too.
Yeah. Okay.
Okay. All right. Take care.
Take care.
Bye.
Good luck.